So now that we collected all the data, let's analyze them. So as I said, the heat of the reaction, Q reaction, is given by the sum of the individual heat of the cold water and hot water. For a closed system, like the one that we explored with our calorimeter, the Q reaction equals 0, which means that the amount of heat absorbed by the cold water needs to be the same that is being released by the hot water if we are in the presence of equimolar amounts, so same amounts of cold water and hot water. So how do we define the heat of a species? We define the heat as the product of the mass times the specific heat and the delta T. So the difference in temperature between the final state and the initial state, okay? Delta T equals T final minus T initial. So here we are exploring water, and the specific heat of water is 4.18 joules per gram per degree Celsius. So how do you define heat? To begin with, the heat is the transfer of energy from a higher temperature object to a lower temperature object. So it's the transfer of heat from an object, let's say at 40 degrees, to an object that is at 10 degrees, okay? So we know that the heat of a species is related to the delta T. So what does this mean? This means that if the delta T is below 0, is negative, our reaction is exothermic, which means that it releases heat because the final temperature will be lower than the initial temperature, and therefore their difference will be less than 0. Otherwise, for an endothermic reaction, so a reaction that absorbs heat, the final temperature will be higher than the initial temperature, and therefore their difference, their delta, will be positive, will be more than 0. So what happens to our cold water, hot water when we mix them? So here we have the first run where we used equal amounts of cold water and hot water. We are assuming that the density of water is 1 at any temperature that we are working with. So the mass of the cold water was 100 grams, the mass of the hot water was 100 grams. The initial temperature of cold water was 20.2 degrees, and the initial temperature of the hot water was 64.5 degrees. So here I did the calculations for delta T using this equation. So the delta T for cold water was 22.1 degrees. Therefore, it increased its temperature, and the delta T for the hot water was minus 22.2 degrees. So it decreased its temperature. As you can see, the delta T is in absolute value exactly the same for both cold water and hot water, only they differ in sign. This is positive and this is negative, which means that the reaction for the cold water was an endothermic reaction, while for the hot water was exothermic reaction. So the final temperature was 42.3, and therefore using this equation, multiplying the mass times the specific heat and the delta T for each species, I calculated the Q cold and the Q hot. And the sum between the two is minus 41.8 degrees. So 41.8 joules, joules is quite negligible. So that could be some loss of heat due to the calorimeter not being exactly a closed system. Remember that it's just a thermos. But again, 41.8 joules is a pretty low heat loss. So these two amounts are pretty equal, which, as I said before, when you use equal amounts of cold water and hot water, the Q reaction should be 0. And 41.8 is pretty much 0 for these types of reactions. Then I used 50 milliliters of cold water and 150 milliliters of hot water. As you can see, the final temperature is higher because I used more hot water, therefore the final temperature is straightforward that it should be higher, right? And as you can see, in absolute value, the heat for the hot water is bigger than the hot water because the mass is higher, okay? And then here we have the data for the third run, 150 ml of cold water and 50 ml of hot water. So the final temperature is lower than here because I used more cold water. So again, it's straightforward that the final temperature should be lower than in here. Now let's analyze the data and the results for part 2. So I collected data for 3 different runs. In runs number 1 and 2, I used the same amount of hot water, 200 milliliters, and in the third run, I decided to use a little bit more, 250. So the goal of part 2 was to determine the heat of fusion of ice, of water. Okay, ice and water are the same thing, only they are in 2 different states. Liquid water is liquid, ice is solid, but it's still water in both cases, okay? So I was curious to see if I would get the same heat of fusion using different starting masses of hot water. In principle, I should be getting the same results, irrespective of the mass of hot water or the mass of ice cubes that I am using, because the heat of fusion of water, in this case, is determined by the number of moles, okay? So it's normalized against the number of moles. So here in this table, I have all my data, the volume of water, of hot water that I used, its mass, again, assuming that the density of water is 1 across all the temperatures, and then the initial temperature of my hot water, and then the mass of the ice cube that I used, the final temperature of my system, and then I calculated the Q bulk water, Q melt warming, and Q ice melting. So, as I said while I was performing the experiment, in this case the Q reaction, which should be 0 at the end, is given by the sum of three individual processes. The first is the Q bulk water, which is the heat released by the hot water due to the introduction of the ice cube and its melting. And then I have my Q ice melting, which is the heat absorbed by the ice cube in order for it to melt. And then I have my Q melt warming, which is exactly the warming of the melted ice. Okay, so let's think about something. While I can directly measure these two, I cannot measure these. There is something else that I can't measure directly, which is the initial temperature of the melt, because it's mixed with my hot water. However, I know that in the instant that the ice is melting, the water that it's just melted must be 0 degrees, okay? Maybe 0.2 degrees Celsius, but it's still approximately 0 degrees. So my initial temperature for the melt will be 0 degrees. So here I calculated the delta T. Remember, delta T is T final minus T initial. The delta T of my hot water, which, as you can understand, is a negative value because my hot water was 70 degrees, 81 degrees, 84, 83 degrees to begin with, and then when I added the ice cube, which has a much lower temperature, of course the final temperature of my water should be lower, okay? So if the final temperature is lower than the initial, then the difference must be a negative value. On the other hand, if the initial temperature of my melted ice cube was 0 degrees, and now the final temperature is in the order of the 70s, then the delta T, T final, minus T initial, which was 0, is a positive value. Therefore, it goes with itself that the heat, that the Q of hot water, of bulk water, is negative, and therefore that was an exothermic reaction. So the hot water released heat, while the Q of the melt, so Q melt warming, is a positive value, and therefore the warming of the melt was an endothermic reaction, so it absorbed the heat that has been released by the hot water. So what can we say about the ice melting? Will it be an exothermic reaction or an endothermic reaction? What do you think? Let's see. So I used the equation Q equals mass times Cp times delta T to calculate the Q bulk water, the Q melt warming, and the Q ice melting using their respective masses, their own delta T's, and the Cp. So the Cp is equal for the water, for the melt, and for the ice, because as I said, they're still all the same thing. They're all water, H2O. So the Cp is 4.18 joules per gram. So here we have our values, and turns out that when I plug in these numbers into this equation, Q ice melting becomes minus Q bulk water minus Q melt warming, because this plus this plus this equals 0. So if I want this, I need to bring the Q melt warming and the Q bulk water on the other side of the equal sign, and they become negative, okay? Negative and negative. Therefore, let's pay attention to the signs, because this is minus, which multiplies this, which is negative. So minus times minus becomes plus. Here I have minus, which multiplies a positive number. Therefore, minus times plus becomes minus. Okay? So this equation brings me to these values for the Q ice melting. So I asked you before, what do you think the Q ice melting is going to be, exothermic or endothermic? So this is positive, and therefore the Q ice melting, the heat necessary for the ice to melt, is positive, and therefore the reaction is endothermic. Okay? So, as I said, the goal was to calculate the delta ice melting, so the heat of fusion of water. How do we define the enthalpy? The enthalpy is nothing less than heat change at constant pressure, and is defined by the Q ice melting divided by the moles of ice. So 6,020 joules per mole is the textbook value. So if you go on your textbook or on Google and you look for the heat of fusion of water, you will find this value. So we hope that our numbers will be close to this. So I calculated the moles of ice that I used, starting from the mass of the ice cube and dividing by its molecular weight. Remember, ice, it's just water, and the molecular weight of water is 18, okay? So this is the number of moles of the ice cube in run number 1, in run number 2, and in run number 3. This is the Q ice melting for these corresponding runs, which I have taken from here. And this is the delta ice melting, which is exactly this amount divided by this. And what I get is 7,355, 6,538, 6,908. The average value that I got with my experiment is 6,934.2 joules per mole, which is pretty close. I am pretty happy of how the experiment turned out to be, because I'm only roughly 1 kilojoule away from the textbook value. So why didn't I get the same value that, you know, scientists in sophisticated labs obtain? Well, first of all, again, remember that we're using a thermos, the one that we commonly use for, you know, to keep our food warm for lunch. So that's not the perfect calorimeter ever. So there might be some heat loss, for example, or maybe I wasn't quick enough when I was measuring the temperature of the hot water when I pour it into the calorimeter. Or maybe for example, didn't wait long enough for the temperature to be completely stable. However, I did. I'm sure I did, so it must have been something else. Maybe I have waited for too long and the final temperature dropped because the system was losing heat. So there are different sources of error. I might have made a mistake while I was measuring the amount of water. Maybe I didn't read the meniscus very well, and I got maybe slightly more or slightly less water than I thought or that I wanted. Okay? So when you analyze your sources of error, you need to be very critical and analytical and think about all of the possible error sources that there might be in your experiment. Anyway, nonetheless, I am very happy of the result that I got because it's only 1 kilojoule away from the experimental value that, people usually get in very, very sophisticated labs.